Good afternoon from me, and my name is Myrsini Maglogianni, and I'm a PhD student at the University of Texas at Arlington. I'm working with Professor Shah, Professor Consta, and Dr. Demoklidis, and today I'm going to be presenting you our work with the title Newly Synthesized Nanotube Hybrids for Sustainable and Multifunctional Coal-Ash-Based Concrete. As we all know, concrete is one of the most, maybe the most used construction material in the industry, and also is one of the larger emitters of CO2. Thus, any change in their carbon footprint will make a great dent on the global emissions. Some people mostly use amounts of fly ash varying from 15 to 25%, and that's also recommended by ACI. Though we all know that fly ash and in general coal ash is one of the largest industrial waste products, and also can be a great solution and very cost-effective in reducing the content of clinker in concrete. So we do have a question, like, can we use more than that 15 to 25% of fly ash in concrete? And if we can, how this can be done? In this research, we evaluated the use of innovative materials. For example, this material here was provided by one of our partners, and it's a really newly synthesized type of carbon nanotubes. It is not just a single additive. These CNTs are hybrid CNTs, and they're grown on situ on a variety of other particles. For example, carbon black, cement, or silicon. And studies in their lab have shown that N-Tech CNTs are less entangled than conventional multi-wall carbon nanotubes. So that started our research in developing high-volume fly ash cementitious materials. In this research, we used two different types of fly ash C and fly ash F, and you can see the composition of those two types in this table here. We used two different dosages of 15% and 13% of fly ash as cement replacement, and we used also ordinary Portland cement and standard sand to develop mortars and evaluate their mechanical properties, namely flexural strength, compressive strength, and Young's modulus, and their 28 days piezoresistive response. First, we evaluated the flexural strength of mortars with fly ash type C and at 15 and 30% cement replacement. We can observe here in this graph that at 3 and 7H, the fly ash mortars show comparable values with the ones of ordinary Portland cement mortars, and at 28 days only a small increase of 5% approximately was observed for this type of fly ash mortars. When we used fly ash F, a small decrease of flexural strength was observed in all three ages, varying up to -6%. As we already discussed, the substitution of cement with supplementary cementitious materials can significantly lower the carbon footprint of concrete. Also, if fly ash is effectively used in cementitious matrices, it can reduce the concrete production by 20% and even more. At the same time, if we use highly dispersed carbon nanotubes in the cementitious matrix, we all know that the carbon nanotubes can act as bridges across pores and cracks, resulting in unprecedentedly increases in mechanical properties. In this research, we used two different types of NTEC carbon nanotubes provided by our partner, and here you see them designated as NTEC A and NTEC C. And as we all know, the sonication, the dispersion of carbon nanotubes is really important in improving the mechanical properties of cementitious matrix. That's why we used both types of CNTs, and we used an ultrasonication procedure developed by Professor Shah and Professor Consta, along with the use of the superplasticizer, and we prepared highly dispersed suspensions, including 0.1% of either NTEC A or NTEC C. The dispersion state of the suspensions was evaluated and quantified during the dispersion and after the dispersion procedure using spectroscopical methods as UVVs and DLS. Here on the left of the slide, you can see results from the UVVs of NTEC as received before the application of ultrasonication energy, and NTEC A and NTEC C sonicated. We observed that NTEC C as received does not they show only a slight peak absorbance here, and that's because the entangled CNTs do not absorb the UVB light. During ultrasonication and at the end of the sonication procedure, we can see that this absorbance around 220 increased at higher values, and this is the result of the ultrasonication procedure that disentangle the individual CNTs inside our suspension. At the left side, right side of the slide, you can see the results from the particle size distribution and the zeta average particle size, the hydrodynamic particle size. Again, here you see results from NTEC as received and NTEC A and NTEC C after the application of ultrasonication procedure. Before the ultrasonication, we observed a high particle size and a very wide particle size distribution, which after sonication became less wide, and also the particle size decreased to about 170 nanometers and 150 nanometers. And we can probably say that these dispersions after ultrasonication, they are nearly monodispersed. From now on, I'm only going to show results related to NTEC C, since both suspensions showed a similar behavior during ultrasonication. We chose the NTEC C to proceed this research with. In this slide, I'm showing the percent change in flexural strength of fly ash mortars compared to the plain mortar with no fly ash substitution. As we discussed earlier, only a small change and probably no impact was observed when fly ash C, 15 and 30% was used as cement replacement. When NTEC C was used for the fly ash C mixes, and a really big increase of 87% was observed for the fly ash CNT mortars. Increasing the amount of fly ash C from 15 to 30 at the CNT reinforced mortars, we observed a 40% increase in their flexural strength compared to plain mortar specimens. Similarly, we observed increased values for flexural strength for both FAF 15 and FAF13 mortars reinforced with NTEC of about 49 and 20% respectively. Here, it is really important to notice that before the addition of CNTs, we have values that are slightly lower than that of plain mortars. Though with the addition of CNTs, a really high increase in flexural strength can be observed. Similarly here, I'm showing results for the compressive strength of fly ash mortars and mortars with fly ash and CNTs. For fly ash type C mortars, a small variance was observed from about 13 to 10 from 10 to 13%. While for fly ash F, we observed the same trend as the flexural strength, even though the values for mortars without the CNTs were lower than that, slightly lower than that of plain mortars. The addition of CNTs increased further their compressive strength. In this slide, I'm showing results for the Young's modulus for mortars with fly ash C. And you see here two different values, and these are values that were calculated during the 4-point bending testing for flexural strength, and also using the strain stress curve for compressive strength. We observed no variation between these two methods, and also, as we also saw for flexural strength, the highest increase was observed for the FAC 15 NTEC mortar of about 78%. Similarly, for mortars with the use of fly ash type F as cement substitution, we see the same trend, and again, a 15% of cement replacement gave us the highest increase in Young's modulus of about 62%. So far, we see that the addition of NTEC CNTs in the cementitious mortars impressively increase their mechanical properties, namely flexural strength, Young's modulus, and compressive strength. Though, owing to their unique properties, CNTs impart new functionalities in the cementitious mortars. Due to their high electrical conductivity, they can increase the electrical conductivity of the cementitious mortars, which is ordinarily an insulator, and also they can improve their stress, strain, and crack detection ability. We started with the evaluation of electrical resistivity of 28 days mortars with fly ash type C and fly ash type F. We observed that for both percentages, for dosages of fly ash, 15 and 30%, there was no significant variation. This is why we choose from now on to just show you one value, which is the average value between the 15 and the 30% fly ash replacement. We observe here that for plain mortar, fly ash type C and fly ash type F mortars, we have really high values of electrical resistivity, and these are attributed to their electrical insulate nature. Addition of CNT for both fly ash type C and fly ash type F mortars decreased the electrical resistivity by 35% almost, and that means that an increased electrical conductivity was observed for both mixes with the addition of CNTs. We continue with the evaluation of the piezoresistive response of mortars with fly ash type C and fly ash type F. These mortars here, they don't have CNTs in them yet, and I'm showing their evaluation of piezoresistivity using the fractional change in resistivity. So this tests were conducted using AC and the two-probe method, a compressive loading, unloading, a compressive load and then loading and loading curves was those specimens were subjected to a compressive loading of loading and unloading cycles. We see here in blue the normalized stress of the loading and unloading cycles of the compressive load. On the bottom here, and you can't really see it, but it should be with red color, it is the fractional change in resistivity of the fly ash mortars. As fractional change in resistivity, we calculated the resistivity in real time minus the initial resistivity divided by the initial resistivity. So this here shows that the plane mortars with fly ash C and fly ash F do not exhibit any ability to sense the applied compressive load. That's why it's nearly close to zero. In order to say that a specimen has piezoresistive ability, we should have a fractional change in resistivity higher than 5%. Here, and showing this this plot here, it's going to be easier for everybody to understand. I'm showing that CNT mortars with fly ash C reinforced with N-Tech at an amount of 0.1% per weight of cement. Here we see a direct, reverse relationship of the compressive load with the fractional change in resistivity. As the compressive load increases, we observe a decrease in the fractional change in resistivity, and then again it returns back to its original value during unloading cycles. With increasing load, the fractional change in resistivity also increased, and we observed a really high piezoresistive signal up to the failure of the specimens. Delta R to R0 of 143% was observed at the end of this experiment, and that shows us the ability of this specific specimen to understand the mechanical deformation induced by the compressive loading during it's recorded by the fractional change in resistivity. We ran the same piezoresistive tests for fly ash type F mortars with N-Tech 0.1% per weight of the binder. We observe here that the mortars with fly ash type C and fly ash type F show a similar behavior, and we observed fractional change in resistivity varying from 7% up to 140% at the end of this experiment. The results of our research showed that we are able to develop mortars and essentially concrete with low carbon footprint by incorporating really low amounts of highly dispersed hybrid nanotube materials. Here I'm showing a graph of the mechanical properties for the fly ash mortars, and we observed a really high increase in their flexural strength and Young's modulus up to 87% and 78% respectively. It is really important here to note that while the mechanical properties are dosage and type of fly ash dependent, the piezoresistivity response found to be independent. It doesn't show the same trend as the mechanical properties. All the mixes tested were showing a really high piezoresistive response, and from that, we can understand that these mixes can be used as a piezoresistive sensor for strain, stress, and crack detecting reasons. Continuing our research, we are going to try a higher amount of fly ash and develop a high volume fly ash concrete by just incorporating really low amounts of this newly synthesized carbon nanotubes, and also develop a concrete that will be also low carbon footprint, and that's it. I'm sorry. Yes. Thank you for your attention, and I want to thank our collaborator CASM that provided our CNTs to us, and also thank my supervisors and collaborators in the Center for Advanced Construction Materials.